Welcome to the Power Edge. This week's episode is coming up next.
Adding just 3 or 4 electric vehicles to a single residential block can reduce the lifespan of the local neighborhood power transformer from 40 years to barely 3 years. Everybody argues about electric vehicles like it is a culture war, but almost nobody talks about the actual infrastructure underneath it all. Can the grid handle millions of EVs? Are gas vehicles actually more practical long-term? And why are utilities, data centers, and AI all suddenly competing for the same electricity? Today, we are breaking down the real conversation behind EVs, the power grid, and what happens when electrification collides with aging infrastructure. Mia, the cultural debate over electric cars, seems entirely disconnected from the physical reality of how we distribute electricity.
The disconnect is staggering. When people debate electric vehicles, they focus on range anxiety or political mandates. They miss the physics of the problem. A typical American household draws about 2 to 3 kilowatts of power during peak evening hours. When you install a level 2 EV charger in your garage, that device alone can pull 10 to 14 kilowatts. Plugging in your car is the equivalent of turning on 4 entire houses at exactly the same time. If an entire neighborhood does that at 6 p.m., the local transformer simply cannot shed the heat fast enough. The insulation degrades and the hardware fails.
That physical bottleneck completely shifts how we should evaluate the EV transition. People treat this as a consumer choice issue, but it is fundamentally a civil engineering challenge. And despite the friction, the shift toward electric vehicles is accelerating. We see lower maintenance costs, fewer moving parts, instant torque, and massive corporate and government pressure driving adoption. Whether people like EVs or not almost does not matter anymore. The infrastructure transition is already happening.
The momentum is locked in because the underlying technology offers distinct mechanical advantages. An internal combustion engine has thousands of moving parts subject to friction, heat, and wear. An electric motor has a fraction of that complexity. Automakers see the long-term manufacturing and maintenance benefits, and they are retooling their entire production lines. Battery chemistry improves every year, energy density increases, and charging networks are expanding globally. The vehicles themselves are becoming highly efficient machines. The vulnerability lies entirely in the power delivery mechanism connecting those machines to the grid.
Let us explore that vulnerability, because the grid problem goes far beyond a single overloaded neighborhood transformer. The issue is not just one EV, it is what happens when entire neighborhoods plug in at 6 p.m. during summer peak demand, while AI data centers and commercial cooling systems are also consuming massive amounts of power. We are essentially forcing a 20th century grid architecture to handle 21st century loads.
We have to look at the sheer scale of the new demands hitting the grid simultaneously. Electric vehicle adoption is happening at the exact moment the technology sector is building out hyperscale AI data centers. A traditional web server rack uses about 5 to 15 kilowatts of power, but a modern AI-optimized server rack requires 40 to 100 kilowatts. According to the Lawrence Berkeley National Laboratory, United States data center electricity consumption could grow from 176 terawatt hours in 2023 to as much as 580 terawatt hours by 2028. In places like Virginia, data centers already consume roughly 25% of the regional power supply.
The convergence of those two massive power draws creates a precarious situation. Utilities already struggle to maintain stability during summer heat waves when residential air conditioning spikes. Adding millions of high-draw EV chargers and gigawatt-scale data centers to that fragile system seems like a recipe for rolling blackouts. This tension naturally brings us back to the advantages of traditional gas vehicles, which offer a completely different infrastructure model. People often dismiss gas cars as outdated, but they rely on a highly mature, decoupled energy distribution system.
Gas stations do not rely on the local neighborhood transformer the same way home charging does. That is a crucial infrastructural distinction. The fossil fuel delivery system operates largely independent of the electrical grid's minute-by-minute balancing act. Liquid fuel is physically transported and stored in massive underground tanks. A gas station can even operate during a widespread blackout if it has a backup diesel generator. This makes the traditional combustion engine remarkably resilient during natural disasters or extreme weather events.
That grid-independent mobility provides a level of security that electric vehicles currently struggle to match. Fast refueling means a driver can restore 400 miles of range in 5 minutes. In rural areas where electrical infrastructure might be sparse or prone to failure, a gas vehicle remains far more practical. The density of energy in a gallon of gasoline is difficult to replicate, and the century of infrastructure built to deliver it provides an enormous buffer against systemic shocks.
We also have to acknowledge the scale of the existing combustion infrastructure. There are tens of thousands of gas stations strategically placed across the country. Upgrading the electrical grid to offer that same level of ubiquitous, rapid energy delivery requires trenching new lines, upgrading substations, and navigating a labyrinth of local permitting processes. The physical deployment of high-voltage chargers often faces delays of months or even years simply waiting for the utility to connect them to the grid.
Yet, ignoring the advantages of electric vehicles based solely on current grid limitations would be short-sighted. There are EV advantages that people consistently underestimate. Beyond the basic efficiency and reduced maintenance we discussed, widespread EV adoption forces a necessary diversification of our energy sources. When you drive a gas car, you are locked into a single fuel type. An electric vehicle can be powered by natural gas, nuclear, solar, or wind, depending on what the local grid utilizes.
The convenience of home charging also fundamentally alters the daily relationship people have with their vehicles. You no longer have to make a secondary trip to a refueling station. For the vast majority of daily commutes, plugging in overnight provides more than enough energy. And this brings us to a fascinating technological frontier. Ironically, EVs could eventually help stabilize the grid through vehicle-to-grid technology, but we are not fully there yet.
Vehicle-to-grid technology introduces a profound paradigm shift. Instead of viewing millions of EVs simply as a massive drain on the system, they become a distributed network of mobile batteries. If the grid faces a sudden spike in demand, or if a local transformer is nearing capacity, software could briefly draw a small amount of power from the connected vehicles to balance the load, then resume charging when demand drops.
The concept changes the vehicle from a passive consumer to an active participant in grid management. A typical electric vehicle battery holds enough energy to power an average home for several days. If utilities can harness a fraction of that stored energy across millions of vehicles during peak hours, they can smooth out the demand curve and prevent the very transformer overloads we discussed earlier. The challenge is that most of our current infrastructure lacks the bidirectional charging hardware and the software orchestration required to make this work at scale.
Which points directly to the real shift happening beneath the surface of this entire debate. The future is not really EV versus gas. The real story is infrastructure. Whoever modernizes power delivery first wins. The companies that manufacture transformers, develop load management software, and build high-capacity switchgear are quietly positioning themselves at the center of the next industrial era.
The modernization of the grid is the foundational requirement for everything else. We need advanced switchgear, smart meters, and localized battery storage systems that can buffer the demand between the grid and the fast chargers. Companies involved in power monitoring, cooling systems for data centers, and grid-scale uninterruptible power supplies are the silent engines of this transition. Upgrading a single distribution feeder to handle EV loads can cost millions of dollars, and the scale of the necessary investment nationwide is staggering.
We're talking about fundamentally rebuilding the circulatory system of the modern economy. The debate over whether a battery-powered car is better than a combustion engine feels almost quaint when you consider the sheer volume of copper, silicon, and capital required to upgrade the transmission lines and substations. Utilities find themselves in a complex position. They have a captive market with guaranteed demand growth, but they also bear the immense capital burden of upgrading legacy systems before they fail under the new loads.
Utilities must evolve from being slow-moving monopolies into highly agile technology managers. They have to implement dynamic pricing models that incentivize consumers to charge their vehicles overnight when demand is low. They have to integrate intermittent renewable energy sources while managing the constant, massive draw of AI data centers. The successful utilities will be those that treat the grid as a digital network rather than just a collection of wires and transformers.
People keep debating the car, But the real question is whether the infrastructure underneath society can evolve fast enough to support what is coming next, because EVs, AI, data centers, electrified buildings, and modern cooling systems are all pulling from the same grid, and most people still have no idea how fragile parts of that system actually are. If this breakdown changed how you view the energy transition, share this episode with someone who appreciates a deeper look into the systems quietly running our world.
Thank you for watching. If you enjoyed the video, please like, subscribe, and share.